Okay, hello everyone. Welcome to the Computational Methods in Engineering. As our final class, we're just going to briefly talk about machine learning and how we can apply some simple machine learning algorithms when we're dealing with environmental engineering data. So as a quick recap of our last class we mainly focused on the sample probability, especially trying to test certain hypotheses, right? So we talked about the student's t-test, which means that when we're trying to confirm whether a sample belongs to a proposed population or when to compare two different populations, we could use the student's t-test, which is calculate the t-value and then further find out the critical t-value and do the comparison. We also said that if the population doesn't follow a normal distribution, people would normally use a Wilcoxon signed rank test, right? So basically, there are ways to calculate the difference and then rank all of the differences and then do the calculations. But eventually, it's similar to the t-test. There's a table for us to refer to find the critical, basically the critical z value, and then to test certain hypotheses. And we also briefly talked about the ANOVA test, which involves the evaluation or comparison of the variances for different sample groups to confirm whether they are coming from the same population. Okay, so this class we're going to briefly talk about machine learning. And of course, machine learning is a very broad topic. Normally in other engineering fields, for example, computer science or computer engineering, machine learning, it could be several classes, right? It involves basic machine learning, regression, and then, for example, deep learning. Especially now, there are large language models, which is very popular, and people think that this is going to be the technology that revolutionize the mankind, right? And we're seeing a lot of the changes nowadays, and you can see the large language models like ChatGPT has been changing or iterating every several months, and then new models are more powerful than the previous models, and people have been applying these models in different exams, and it looks like they're performing really well and better, right? So this is something that could eventually change how we see different disciplines and also for our environmental engineering field. So that's why I feel that it's quite necessary for us to at least understand what is machine learning from some basic examples, and then to basically see that this is not something that's really far away from our discipline. Okay, so first, what is machine learning? Right, so we hear a lot about machine learning, especially I think maybe this term mainly from 10 years ago, maybe 15 years ago, when people first applied or used a machine to beat a Go player, which is sort of a chess game that's very popular in Asia, right? So people think that, well, at that time, people regard the chess game as the most sophisticated game because there are all the different types of possibilities. And then it depends on the human's memory and also experience and accurate evaluation of the status, right? So the basically the status of the chess game, right? But it turns out that the machine, which relies on the deep learning, could eventually beat the best player in the world, and which is a very big news. So in the beginning, I think the machine learning player, which is called the AlphaGo, so it beat the famous at that time the top player from South Korea by 4-3, right? But then several months later, it just beat the player like 4-0, and basically there's no way that human can compete against the AlphaGo anymore, and because they have been reiterating using developing newer algorithms very quickly. And then I think at that time people started to understand or started to notice, well, this machine learning could be changing a lot of fields. Okay, so you can use the human learning, or we can use the human learning as a comparison or as an example to talk about what is a learning process. Right? If we think about the human learning process, we learn from introducing some basic concepts, right, and then do practice, like trial and error. So if we do it correctly, then we say that, well, we have mastered this knowledge. If we did it wrong, then we will practice similar problems until we actually understand or master this knowledge. right? And then later on, we could, let's say we could have experience from different fields. For example, environmental engineering is a combination of the knowledge from different disciplines, like chemistry, physics, mathematics, right? So different knowledge merged together. Then they form our experience. And then eventually it goes to our brain and then serve as an instinct, right? So we can do some prediction even before we actually do all the calculations, right? So actually, machine learning is trying to use a similar method to sort of simulate human learning. So we just provide a lot of data, a lot of basically experience or examples, right? And then let the machine to learn by itself. Of course, there is going to be trial and error. As you can see here, I also put the logo of iReady, right? Because now this is sort of the a homework program for I think K to 8 kids. So right now, my son is also in kindergarten, and he has to do 90 minutes of iReady. And I see that basically, if they do any problem wrong, they will um, keep practicing on these problems until they can pass them, and then they progress to the next level. It's sort of this is how we learn, right? So this is a trial and error process, and for machines, we're also applying this trial and error process to let it learn by itself. And that's what we call as machine learning. So more rigorously speaking, the definition of the machine learning is shown as follows, which is the development and study of statistical algorithms that can learn from data, right? So there are examples or data, right, already over there, and then generalize to unseen data. So basically, we're trying to form some experience or let the machine to form some experience, learn from the data by itself, right? And then form some instinct, right? And thus perform tasks without explicit instructions. So basically, we're letting the machine to do some learning so that although there's no equations getting involved, so basically we're not providing direct or clear instructions, but once we train the machine with all of these data and it forms this experience, then we can just, like human learning, we can provide new data and then let the machine to do some work for us, right? So you may say, well, what are the applications of machine learning? So are there examples that we can really trust the machine learning to help us perform tasks even without explicit instructions? And actually, nowadays, there are a lot of machine learning examples. And so, as we said, machine learning is revolutionizing our world, right? So here I'm just giving you a few examples. For example, the health monitoring, I think this is a major area because we know that people treasure their health, right? So machine learning is already helping the hospitals or the clinicians to perform a lot of tasks. So the examples I give here are signal and image analysis. For example, we could be listening to heart rate, and then traditionally we have to rely on physicians, right, to doctors, right, to listen to our heart, and then based on their experience, they can tell, well, whether there are any issues with the heartbeat, right? For example, there could be murmurs in the heartbeat, which means that there are some noise in the heartbeat, right? So then there could also be different frequencies, right? Heart rate variance associated with the heartbeat that can further relate to some health issues, right? Magnitude, how loud the heartbeat is, and also the interval of the heartbeat, so on and so forth, right? So now with machine learning, we could actually train the machine to learn from the data of the healthy people and learn from the data of the basically the people with disease, right? So we can train the machine learning algorithms so that if we provide new data, let's say a new patient having a different set of like new heart rate, right? So the machine learning algorithms can directly tell whether the heart rate belong to a healthy person or belong to a person with certain disease, right? So similar thing, let's say the image analysis, we could do a lot of CT scans, right? We have the CT scans of healthy people, we have the CT scan of sick people. Then based on the, let's say, especially about tumor identification, then based on the size, the shape, the color, the location of these blobs in the image and also the background information, right, on the image, then previously people have been using physicians, right, clinicians or doctors to rely on them to analyze these images and then tell whether the patient has tumor or not. What's the likelihood of having the tumor? And then people do biopsy, right, further to confirm whether there's tumor or not. But now with all of these data on healthy people and sick people, right? So the machine learning can learn from these different parameters and tell the probability of whether it is indeed a tumor or not, right? So you can see basically we feed a lot of data to the algorithm so that it can learn by itself and then make predictions. So actually these different parameters that we show over here, right? These originally are coming from the human experience, right? So we're providing some guidance, but we're not providing an equation. So for example, there's no equation that's telling you the magnitude, let's say multiplied to the power of something. So there's no clear mathematical equations, but then we're trying to let the machine to decide how these parameters interact with each other, right? And then also how they eventually determine the likelihood of having heart disease or likelihood of having tumor. And for each of the parameter here, we actually call them as a feature, okay? So if we let the machine to learn based on all of these features that we already defined, then we call it as supervised learning. As you can see, we're providing some instruction, but we're not providing a clear instruction, right? So this is supervised learning. It could also be that we don't provide any of these features. We just let the machine to analyze the image, right? And then to just learn by itself and then identify what are the parameters that are the most important, right? So then that's called the unsupervised learning. We're going to talk about these categories later on. So another example is object recognition. So object recognition, I'm using self-driving as an example, but also you can think of image analysis as or tumor identification as the object recognition, right? So if you think about driving a car, if it's a person driving the car, if we're trying to avoid certain collision, we'll look in front of us, right, to see the size of the object, the shape of the object, because size and shape determine the type of the object, right? Whether that's a human or dog, a car, a truck, right? And there's also speed of the object, right? The direction of the object, so that with all of these information or these features, we can tell what object that is. And then for self-driving, the car can tell or categorize, right? If you have been in a Tesla before, sometimes I took an Uber and then the driver is driving a Tesla. You can see that basically based on the vision of the camera on Tesla, they can tell what type of object it is, right? You can even see the shape of the object. And that is basically the object recognition. We can also do weather forecasting, especially, for example, here in Florida, we have quite frequent hurricanes, right? So it's very important to forecast or to predict where the hurricane is headed to, because that's not only dependent on the wind. And even for the wind, we have to sort of predict what is a wind pattern, right? So basically, it's going to be a series of parameters. For example, sea surface temperature. This really determines how significant the hurricane will turn into, because if you have a higher sea surface temperature, then there's more updraft, right? The uplift of the air, and then you're going to form a stronger or a bigger hurricane. The size of the hurricane, right? The wind of the hurricane, or the wind nearby the hurricane, right? And then also other type of parameters, relative humidity, right? And then the water vapor concentration and so on and so forth, right? Or pressure, right? So basically we can train the model or the algorithm to utilize these data, right? Understand these features and then try to predict where the hurricane is going to. And in terms of our daily life, for example, when we're trying to forecast the energy load on a city, right? So we can further provide data related to the season, the time of the day, and then basically population, right? And then different certain events, right? And also there could be scenarios where we lose power. If we lose power, we want to analyze what's the reason for losing the power, right? So that later on we could use the data we learned to reduce the occurrence of this power outage. Stock market prediction, right? This is more in the financial realm, Basically, you can analyze all the data that's available on like second to second basis, right? So the trade amount, the performance of the company, and so on and so forth, and to predict how that's the stock perform. And then, of course, large language models. This is a very important tool nowadays, right? So I think everyone use that ChatGPT, Grok, or Gemini, so on and so forth. Okay, so these are the examples of machine learning. But if you summarize all of these examples or problems, you can see some common features, right? So of course, these are important problems, but we also use machine learning when we have to consider the following criteria. First, the solution is too complex for handwritten rules or equations. And if you think about all of these examples, it's quite complex, right? So we can't really have a equation that determines the probability of the heart disease based on the parameters like magnitude of the heartbeat, frequency, interval, noise. Everything is based on experience, right? There's no like a power law or like a log or exponential terms associated with each of the features. Tumor size, the same thing, self-driving, right? Hurricane, the prediction, so on and so forth. This is difficult for us to come up with a handwritten rules or equations. Of course, people try to use that, but a lot of times it depends on the experience, and there is probability involved in this process. So also the solution needs to adapt to new changing data, and this is indeed the case because we're not only focusing on the data in the past, we're also looking into the data in the future, right? So in the future, it could be an extreme case, right? For example, like for self-driving, there could be scenarios. Nowadays, people also use drones, right? So if the drone show up in front of the vehicle, then we have to include these drone features into the learning pool, right? So we have to train the new data associated with the drones, or let's say, for example, there's a balloon and so on and so forth. These new data, we have to train the algorithm with new data. The solution needs to adapt to new changing data, right? This is when we use machine learning. And one important criteria for using machine learning is that we also need to have a large amount of data. So people call this as the 10x rule, the 10 times rule. So basically, the examples or the data that we have, the amount of the data that we have for a machine learning algorithm has to be large enough so that we can generalize certain learning outcomes. So basically, you need to have 10 times more examples than features. So what that means is that now if you look at the heart rate example, here we're listing 4 features, right? So to properly train a machine learning model, you need to have, and what this means that you need to have at least 40 examples of the heart rate, right? And then associated with these 4 different features. So basically, if you think about it in a matrix form, right? So you're going to have basically 5 columns, right? The first column will be the heart rate, right? Or basically 5 groups of data. First group is going to heart rate, second group, magnitude, frequency, interval, and noise, right? So basically, you're going to have at least 50 examples, right? So tumor size, if you have here, you have 5 features, right? So then you have to have at least 50 results. And a lot of times, we're not limited by the data size. If you think about how many samples of heart rates that a hospital listen to every day, right? How many tumor images the hospital analyze over a year, right? Over several tens of years. I would say there could be millions of these data, right? So then this is going to be the proper data pool that we can use to train the machine learning algorithm. The same thing for driving, right? If you drive a car, you can see at least hundreds of cars every day, right? So then this involves, basically, we can use these data to train the machine learning algorithm. So if you recall earlier in our class, we had an example. This is related to the case study, right? So we're trying to create a problem or try to solve a problem that basically output the price of certain flights, right? So basically, it's asking the user to select the city from certain that the traveler wants to go, for example, Boston, Denver, Honolulu, and then we create this switch case structure that if it's the case 1, which is Boston, then it's 345. If it's Denver, 150. And then if it's third one, stay at home and study. right? So basically it's unavailable, right? But if you are an airline company, right, that basically have the decision or have the power to decide the price, are we going to use such a simple algorithm? No, because airline company wants to make money, right? We cannot just make it so simple that you select certain city and then it's just going to give you a fixed price, right? You can imagine if you are from, let's say, nearby Denver area, let's say from the Midwest, then this makes sense because you fly to Denver, it's cheaper. If you fly to Boston, it's more expensive. But if you are from Boston, right? If you're from, for example, from New York, right? So this price doesn't make sense at all, right? So if you're an airline company, you have to consider what are the factors that's involved in setting up the price, right? And nowadays, as you can see from the news, the airline companies are using machine learning algorithms to set up or to decide what price they should list when we're searching for flights, right? So of course there are many factors. For example, as I mentioned, the destination, right? The location of the traveler, right? Basically the origin, right? The location that you're flying from. And of course, it also depends on seat type, the data, I mean the date of the booking, because if it's during the traveling season, then the airline companies wants to use a higher price, right? The time of the booking, right? So normally people become more available overnight, right, in the evening. So then if people search for price more frequently in the evening, then airline companies will use a more expensive price, a higher price, right? If it's during the day or let's say early morning, over the midnight, right? The price, if you check, if you tried on the different airline company websites, actually the price is cheaper. Availability of the seats is for sure, right? It's sort of similar or related to the date of the booking, right? So if it's during the Thanksgiving holiday, then definitely there's low availability of the seats and the price can be higher. And also availability of other airlines, basic competitors. So if you are traveling to Boston and then at the same time there are 10 more airlines that are operating in this line, then the price cannot be really high. Otherwise, you cannot sell your ticket, right? So the number of seats. So yeah, so basically the how big your airline is, right, etc. So basically, these are all the different features this airline company can consider, and then you can use all of the data that you have obtained from your past years, right? And then analyze basically what is a profit, because eventually you want to enhance or increase the profit for operating the airline. And this is a perfect place for using machine learning to set up the price. Although I would say it's using machine learning against the customers, right? Because now we have to suffer from the higher price. But I mean, this is how the company will make profit and then support the workforce, and that is understandable. So as you can see, the solution for this example is too complex for handwritten rules or equations, and we should use machine learning to solve this problem. And in terms of environmental engineering, how can we use machine learning? So here are a few examples we can consider. And I have to say that this result, when I Googled for it, or some of these are quite common problems, right? And some of them I have to Google. And then actually now you know that the first item shown on the Google page is actually the machine learning generated results from the large language model, right? So for example, I mean, these are the examples that we actually encounter in environmental engineering. For example, the water and air quality, right? You can use machine learning models to forecast the pollution levels, analyze emission data, predict water quality issues, and these models also outperform traditional models. So climate and weather, we talked about the hurricane, right? So if you can accurately predict the past passage of a hurricane, you can also predict the challenge that it creates onto the water management facilities, water resources engineering devices, right? So then it's related to environmental engineering. So basically the models can analyze the satellite data for climate predictions and weather forecasting, enhancing the accuracy in climate change models. And also the weather models. So you can also more accurately predict the infrastructure failures. It can be used to detect pipe bursts or identify locations of the leaks in water distribution network. So what it does is that if the pipe bursts indeed happen, and you can basically analyze the data, let's say you have 200 or 300, let's say 1,000 examples of the pipe bursts, then you can gather the data before the pipe burst, right? For example, they can be related to the time, to the temperature, to the relative humidity, and also to the flows, right? The operating parameters of the water treatment facility, and learn from those data so that in the future you can avoid the problem, right? So learn from the data, and then you can have this algorithm that monitor or input all of this data, and then it's going to predict what is the likelihood of having the pipe burst, right? And then you can also try to prevent the pipe bursts, okay? So here, I just want to basically talk a little bit more about machine learning and basically what type of problem that we're trying to focus on and different categories of machine learning, and then how we should perform the machine learning. And eventually, we're going to go through two very basic examples. So machine learning, as we introduced, it uses data and produces a program to perform a task. So this task that's shown here is human activity detection. So for example, if you wear an Apple Watch or wear some other watch, for example, from Samsung or from other different types of devices, and now you can see that based on your movement, right, your activity, it can tell you, or it will ask you whether you are running, whether you are doing indoor exercise, whether you're bicycle, right, riding a bicycle, whether you're sleeping, monitor your sleep quality, and so on, right? So previously, if you consider how these watch or these personal portable devices monitor the human activity before machine learning time, if you think about the algorithm, right, for trying to write a machine learning, write a MATLAB program to predict the activity, then you have to use these accelerometers to sort of capture the accelerometer data. If it's, for example, this should be the wrong equation. If the acceleration is smaller than certain magnitude, then you set that as the sitting condition, right? If the acceleration is, for example, in certain range, right? This is x acceleration, y acceleration, z acceleration. If it's in certain range, you categorize that as standing. If it's in another range, you categorize as the running, or let's say if the speed is getting faster, then it could be riding a bicycle. If it's even faster, it could be riding a, let's say the riding a car, right, inside a car or inside airplane, so on and so forth, right? So before machine learning, we actually give or set up these strict standards and then categorize the different cases, right? So we can use the if structure or the case structure, and then it's going to distribute the different activity into different groups, right? But you can see that here, a lot of these cutoffs are very, very strict, right? So there could be borderline cases where you could be sitting in a car and then it would think that you are riding a bicycle, right? If the car is having a traffic jam. So if you use these parameters, these strict boundaries, then it could have trouble in identifying certain borderline cases. But on the other hand, if you use a machine learning algorithm and then collect all of these feature data and then just generate as much data as possible, you give it to volunteers, distribute to, let's say, 1,000 volunteers, and then every day they record their status, right? And then also monitor what activity or write down what activity they're in. And then this is basically a perfect example of the machine learning problem that is going to predict that category, right? So it's related to the basically a decision tree. We're going to talk about decision tree later on. So basically, it's trying to predict certain category, right, based on the inputs of certain data. Right? So instead of using a formula, handwritten equation, we're using machine learning to sort of let the machine to learn from the data by itself to form an algorithm, right? So for this algorithm, there's no clear equation, that lead to the output or the result of this activity type. Okay. So then there's also different types of machine learning. I sort of covered this earlier. So you can, based on the what type of data we're providing to the machine learning algorithm. So if you have a certain type of, let's say, the feature data, right? So for example, the size or the, let's say, the color of the tumor, right? So we're providing these feature data, then we call that as a supervised learning. So if you are just providing the algorithm only with the data, for example, only the data of the, let's say, of the, for example, only the outcome data, right? So then it's going to try to identify what are the major features for you, and then ignore the unimportant features. So further, in the supervised learning, there are two different type of problems. One problem is a classification problem. So basically, this is telling the different types of the activity is a classification problem. And if you talk about environmental engineering, whether the pipe burst is a classification problem because there could only be bursting or not bursting, right? The location of the leaks is also location A, B, C, D, right? So this is category or a classification problem. But there could also be numerical, right? So for example, we're trying to predict the level of the air pollutants or the water pollutants, right? So the level is not A or B, yes or no question. It's the concentration, right? Could be any level, any type of value. So then we call that problem as the regression problem. So the output is a real number. It could be temperature, stock price, so on and so forth. So for unsupervised learning, basically people focus on the clustering a lot. So instead of providing an output, it find the natural groups and patterns from the input data, right? So to separate them into different clusters. And then for each type of the problem, there are different, there are different algorithms or different machine learning methods. So for example, for the classification, there are support vector machines, discriminant analysis, naive Bayes, nearest neighbor, regression method, linear regression, GLM. For example, the regression tree. We're going to talk about the decision tree, regression tree later on as the simple example. Okay, so clustering, there are even more different types of machine learning, neural network, machine learning algorithms. So each of these algorithms can be used for a certain type of problem. And I think if you want to know more about these different algorithms, it's better that you take another separate class about machine learning, for example, from computer science, computer engineering. Okay, machine learning also has its own workflow. So for example, you have to first access and explore data. You also have to pre-process data. So what it means by pre-processing is that you remove the redundant data, you remove the data you don't want, right? Data reduction transformation, right? Working with messy data, right? And then extract certain feature, like for example, the size, the color, the object, right? So the velocity, the speed, so on and so forth. And then we develop predictive models. So you can use machine learning, you can optimize parameter, you can also, we should also validate our model, right? So that's why we need to basically separate our data into the training set and testing set, right? So training set, people normally use 70% for the training set and 30% for the testing set. So basically you use 70% of the data for just training the algorithm, and then the remaining 30%, you use that to verify whether the machine learning algorithm is correct or not. And then eventually, after we get the algorithm, we'll integrate the results into some software and do the, let's say, to sell it, right, to commercialize it. So here, as I said, we're going to talk about some basic examples of machine learning, and because we talk a lot about like machine learning, how we can do that, and then what are the applications, but we really don't know what exactly does it mean by machine learning, right? So for example, if we provide the machine with certain data, let's say for this example is a classification example. So let's say that we have two features. We're talking about the heartbeat, right? So we're trying to look at the magnitude of the heartbeat and also the frequency of the heartbeat. right? Of course, there are more features. Now, let's just imagine that these are the two features that we're looking at. And then this is a classification problem. Basically, it means that, well, if x-axis is the heartbeat magnitude, how loud it is, y-axis is a frequency, and then basically it's telling us, right? So the red dots means that the person doing the heartbeat test is sick. Green dots means that the person doing the test is healthy, right? So then this is a classification problem. And we're trying to develop a machine learning algorithm that basically to let the machine learn by itself. Because, well, if it's human experience, we can tell that, well, maybe we set up certain boundaries, and then if it's within that boundary, then it's okay. But the thing is that if there are even more features, not we're only providing two features. If there's one more feature, right, then we basically put ourselves into a difficult, challenging situation. And we have to set up more boundaries, more criteria, and the more features you have, the more difficult or more challenging it is for a human to analyze this task. So here we're just using this very simple two-parameter classification as an example. So how do we classify our data, right? So if we're doing it by ourselves, right? So we would say that, well, let's first draw a line. Let's assume that this is x0 and this is this white line, horizontal white line is x0, vertical white line is x1. So if we draw a line of x smaller or equal to -12, right, each of the block represents 5, then you can see that, basically another thing is that here on this image, there are 10 green dots and 10 red dots. And our goal for the classification is to develop an algorithm that can separate these data, right, to classify them into different groups. So first we can draw a line x equals -12, and then you can see that we categorize the group into the left-hand side and then a group onto the right-hand side. I would say that this classification is quite successful, right? You have sort of a pure group, and we call this group as the leaf. We're talking about decision trees, right? There are branches and there are leaves. When you get to a leaf, that's the end point of a decision tree, right? So we want basically the faster we get the leaves, the better. Okay. So x0 minus x0 smaller than -12 seems like a good classification, and then it can generate us a leaf node, right? And on the right hand side, you have this still a blob of data, and then the other criteria we can use is, let's say, x0 smaller than 9, which is a line over here, right? So if it's the case, then we sort of separate the data on the right hand side, and then you have this pure mode on the right hand side, 4 data points, and then you have a bunch of data points over here. And then further, you can based on x1 to split the data. x1 larger than 9 or smaller than 9, you can now basically separate all of these data. You have this algorithm that split data into pure leaf nodes, right? So this is a classification that, let's say, if we assign this task to a human, then this is what we can get from here, right? So then it comes to a question. Let's say this is the way that we do the classification, but why did we do this classification, right? So why don't we put the first line in the middle, right? Just use x smaller than 0 as a classification criteria, or as this criteria for splitting the data, right? So this is basically from the human experience, because when we say that we want to separate data apart, we want to get a group of data that's pure, right? And if you show that in a mathematical way or a physical way, thermodynamical way, right? Basically, we want to have a group of data that has a low entropy, right? So entropy shows the randomness, right, of the data. So if we have a low entropy, then it means that we're doing a successful classification. So then, are there ways to, let's say, mathematically quantify the entropy of the data, right? So basically, this is how we can calculate the entropy of the data. So if we're comparing different types of the decisions, right, different types of the criteria we want to use, let's say these are two different ways. For example, the first one is y smaller than 4, which is a horizontal yellow line here. You can see that y smaller than 4, x1 smaller than 4, then you're going to have the split like this. X0 smaller than 12, we're going to have the result like this. So if I ask you which split is better, you'll definitely say that the second split is better, right? But is there a way to quantify the betterness, right? The basically quantify why this split is better, right? So people define this information gain or this IG parameter. So to define or to calculate information gain, as I said, we need to first quantify the entropy, and the entropy is calculated by the summation of the probability of certain class. So we have class 1 and class 2, or class A or class B, multiplied by the log. Basically, this is log 2 of that probability. So we can show that in mathematical way. So for this case, how do we calculate the information gain? And basically, if we put it other way, how do we calculate the entropy for each of the category, right? So if we just consider the x smaller than 4 case, right? So we can calculate the entropy of each group over here, right? So basically, if we just look at the entropy for this split over here, there are 14 data in total, and the other side, there are 6 data, right? 14 data points, and then there are 8 data points that are category green, and then 6 data points are category red. So then you can calculate the entropy. Let's say this E1 being minus, so you have 8 green cases multiplied by log 2, 8 over 14, and then minus 6. Right, this is the entropy for the first split. And then you can similarly calculate the second one. There are 6 data points, so it's 2, 6, 2, 6, and then 4, 6, 4, 6. So then this is basically the entropy for the other group. And then you can also calculate this one, right? So for this one, it's going to be, let's see, this is E1, and then this is E2, right? And then for E3, it's going to be minus, we don't need to, basically, you can also consider the green group, right? But the green group, the probability is 0, right? So if it's 0, then basically we don't need to consider that. And then if it's 4, then you have minus 1 and multiply by the log of 1, right? Log 2 of 1. So basically E3, the entropy is 0, right? Which means that it's lowest entropy, which makes sense, right? So E4 is going to be so there are 16 data points, right? 10 green and 6 red. So it's going to be 10 divided by 16 multiplied by log 2 of 10 over 16 minus 6 over 16 multiplied by log 2 of 6 over 16. Right, so this is the E4. So then you have these different, basically the different entropy groups, right? So with that, you can calculate, you can basically calculate, let's see, E2, E1, E2. So E2 should be this one. So 6. Right, so with, yeah, so you see, basically this should be E2. Right, so E2 has an entropy of 0.91 or 0.92. E1 has an entropy of 0.99. This is 0. This is 0.95, right? E4 is 0.95. So you have these different entropies, and then information gain is just the entropy of the parent minus the basically the two weighted entropies for the children, right? So basically here you have, as we mentioned, 14 data points. Here you have 6 data points. You use 14 multiplied by 0.99 and 6 multiplied by 0.91, right? So then the entropy of the parent, you can also calculate that. So that's going to be E parent, right? So if you have an even split, then you have 0.5 multiplied by log 2 of 0.5. And then you just do minus this thing and then multiply by 2, right? So we choose 1. So when you have an even split, the entropy is 1. So you use the entropy of the parent minus the weighted summation, weighted sum of the entropy for the child, and then the information gain from the split, as you can see from the first split, is going to be 0.034, and the entropy or the information gain from the second split is going to be 0.24. And then if you compare the two information gains, right, the second split is better, right? So then what does machine learning do? Machine learning is actually going to run through all of the different splits. So you can see it's a trial and error process. It's actually also a pretty brutal method. You just try all the different the classifications, right? And then see what information gain you have. When you have the highest information gain, then it's going to use that as a criteria to classify the data, okay? And then after you classify the data by one way, and then it's going to set up the other classification and run through the trial and error process again, okay? So keep trying the different scenarios of the information gain until it basically classify all of the data. So this is what's called machine learning, right? So you do a lot of trial and errors, just trying to get the highest information gain for the classification. And then you may also imagine, well, how do we categorize the data when we are, or how do we learn from the data when we're trying to solve a regression problem? So we were talking about the classification, which is either 0 or 1, yes or no. But in the regression type of scenario, we're trying to look at the values, right? So we're trying to predict the concentration of the pollutant. It's not a yes or no answer for the concentration of the pollutant. So this is another example. For example, we're trying to predict the pollutant concentration, again, based on these two features, X0 and X1, right? The color here represents the data, right? So then you can see that the original data looks like this. You have a bunch of yellow, you have a bunch of red. Red means higher value, yellow means lower value. Then you can split the data, right? X smaller than -7 or X1 smaller than -12. And then you eventually split all of the data into these different groups, right? So then we achieve our goals because now for different groups, their data are in similar magnitudes, right? So then if you have certain value, let's say X equals -10, right? It will actually go X1 equals -10, then it will actually go to this group, right? And then look at -10, it goes here, right? And further means that it's going to take one of these two between these values, and then you can do linear interpolation to find to predict the value. Okay, so we said that we could use information gain to calculate what is the benefits, right? These benefits of different classification. But how do we define information gain here, right? Because now we're not talking about 0 or 1 cases. So we could actually define this information gain in a different way. So which is related to the variance reduction, right? So when we split the data based on values, we actually want a split that has a smaller variance, right? Which basically means that within this group, all the values are similar, right? This is a goal for doing the regression, right? If we know that if the value satisfies certain standards, we can directly put the data in over here and then analyze what's the data here, right? So this is the basically the fundamentals for the regression problem, that is to reduce the variance for the system or for the different groups. And then you can also calculate the different splits, right? So you can basically the variance reduction, or it's going to be the parents' variance minus the weighted sum of the children's variance. And then eventually you can see that the variance reduction for this first split is 3,000 or close to 4,000. which means that the first split is going to be better, right? So here I just give two examples on the decision trees, right? So you could have the classification decision trees and regression decision trees. Classification cases uses the information gain, while the regression problems use the variance reduction. And this is just one type of the algorithm. You can also use different types of algorithms for other types of the problems, right? So there are vast types of different machine learning algorithms that we can use. So finally, let's do a few exercises. So we have been learning about MATLAB through our semester, and actually these problems are coming from the MATLAB examples. But you may also have heard that nowadays people use Python a lot for machine learning purposes, mainly because Python is a free software, and there's also an active community that's sharing their code, and people can try these different types of new algorithms. So the fundamental programming methods behind MATLAB or Python are similar. But since we have been working on MATLAB throughout our semester, let's just work on these examples with MATLAB. So the first example is analyzing the radar data. So radar is trying to analyze the ionosphere of the atmosphere, which is basically the atmosphere that's really far away from the Earth. Right? So using the radar to analyze whether the data that the radar obtained is correct or not, right? So there's also a link for this data here, right? So you can see ionosphere, this is coming from the UC Irvine Machine Learning Repository. So it consists of certain data, and then it's labeled as good or bad, right? So good or bad, this is classification. And if you look at this data here, we can go to the example. This is actually example 1, and then let's load this data. Okay, so this is the loaded data. You can see that the X data, which is basically our feature data, right? So you have different columns, and then these are different values that you get from the radar, right? And then some are 0, some are 1, and then the Y is the category of good or bad, right? So they're good or bad. And you have 351 data points, and then let's see if it satisfies the 10x rule, right? You have 34 features, right? 10x rule is 340, right? You have 351, which means that it's okay. So then how do we do a decision tree, use a decision tree to analyze the data, right? So basically in MATLAB, you use the fit C tree, right? Fit, basically you're trying to fit the data. C is classification, and then tree is decision tree. And then you put the feature data and then the outcome data or the result data over here, right? So then you can run through the problem. So now we get to now we already run it. You see the TC, this classification tree. There are different algorithms talking about the node where you make the cut and so on. So actually you can show the decision tree. You can just view this decision tree. This is the model results, right? And then see, this is our decision tree. Okay, so basically it's classifying the data into good or bad based on, you see, X5, X27, so on and so forth, right? So this is our decision tree. And then you could also try to see what parameters play a more important role in influencing the decision tree. So you can see that parameter number 5, which is in the X table here, the 5th column will have a major influence on whether the data is good or bad. And then the data 25, 20, 27 also has a pretty significant influence on our data, right? So you can imagine if we are trying to solve this problem by hand, right, and we have 34 different features, we have to first sort of plot the regression, right, the correlation between the data and good or bad, especially good or bad. You can't show that in a linear way. So you can't really plot or calculate the R-square out of these plots. But by using the decision tree or this classification decision tree, you can identify the parameters play a major role and also sort of set up the criteria. And then you can also with this algorithm, you can also predict the data. We're going to talk about the prediction in our second example. So the second example is trying to predict the mile per gallon of a vehicle, or the MPG. The mile per gallon, nowadays, a mile per gallon of vehicle is relatively high compared to, let's say, 20 years ago, because 20 years ago, we don't have very good internal combustion engine technologies, right? Also depends on the size of the car, the weight of the car, so on and so forth. So then how do we find parameters that influence the mile per gallon most importantly, right? And you can see that the mile per gallon is a numerical value. It's not a yes or no question, right? So then this is our second problem. So we can load our data. So this is load the car small data. This is, I would say, original data set that's in the MATLAB. And then you can see we have different parameters or features. We have acceleration of the vehicle. We have the cylinders, how many cylinders the vehicle has, right? So 8-cylinder, 4-cylinder, right? Displacement, horsepower, right? And then let's say manufacturer, compare different types of the vehicle, model year, right? Model. So all of these different types of data. Of course, the most important data that we want to show is the mile per gallon data, right? Origin, weight, and so on and so forth, right? So basically, now the problem is, well, can we identify the feature that is most important? Now, how can we predict certain mile per gallon value if we just provide, let's say, the weight of the vehicle or model year of the vehicle and so on and so forth, right? So we can put all of our features that we want. We can put model year, weight, right? Acceleration, cylinders, horsepower, so on and so forth. Let's just put 5 of these, right? So there are 5 features, and then we can do the decision tree calculation again. And then you see, instead of using a fit C tree, we use a fit R tree, regression tree, and then you can view the result for your decision tree. Okay, so we can run this code, and then this is our decision tree. You can see again, basically we're splitting all of these parameters. Eventually, we get these different groups of data that has the lowest variance, right? And then you can also show the feature importance. Okay, so this is our feature importance. As we said, there are several parameters: model year, weight, acceleration, cylinders, number of cylinders, horsepower, right? So you see that basically the weight is the most important one, right? So it has the highest bar magnitudes, right? And then the year also play a role here, right? So then let's try to shorten that into 2 parameters. Okay, we'll run the code again. And then show the results. Okay, so this is our feature importance. This is our decision tree. Again, splitting the data in different way. Now you just have 2 parameters, so that just involve x1 and x2, right? So then the problem is, well, if now we have a new vehicle information, right? So how do we predict the MPG, right? Mile per gallon. So we said that, well, if you look at the model year, right, you have different years of the model, right? And also you if you look at the weight of the vehicle, right? This is a weight of the vehicle, right? So now let's say that we have a new vehicle that has a weight of 4,000 pounds, and then model year is 85. So with the model, we can just use a predict function, right? So we can predict using the model and the 2 parameters to predict what is the mile per gallon, right? 14.333, which is quite small. But if you have a lighter car, then you're going to have a higher mile per gallon, right? So this is how we can use the model to predict certain regression or the result of certain regression problem. Okay. So the third example is the demographics data, right? So people always analyze the census data and trying to identify certain patterns. Let's say we're having this demographics data. This is actually the data that's collected from the Twin Cities, Minnesota. So if you can see, it involves different locations, basically different zip codes, and then it also shows the demographics, right? So socioeconomic parameters, percentage of female, male, age to 14, percentage 15 to 64, 65 plus, college degree, right? College degree and above, right? High school degree, less than high school degree, and then the household income. So then we're trying to see, well, are there parameters that are going to play a role in the household income, right? So then how do we, I mean, this is a data that we got, right? So how do we find out certain features that play the most important role in determining the median household income, right? So then we can copy all of the data. So first, one thing we want to identify is that, well, we have how many features? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 features. But we only have 45 results, so which is not a perfect example for using the machine learning algorithm. But anyway, we can still use it. So we can copy the data over here, sort of have some code already over here, but let's just copy and paste again. Technically, it's easier if you incorporate everything into a M file, so it loads the M file. And as we can see earlier, if it's a regression problem, we use the fit R tree, and then we use the feature data from the first column to the column before the last one, and then basically the result data is going to be the last column. And then you can do the same analysis. Okay, so you can see that the feature that is the most important in our analysis, right? This is decision tree. That's the most important in our analysis is actually related to the education, right? So the higher the education of the high school degree, right? So this is, well, let me see, 1, 2, 3, 4, 5, 6, 7, 8, right? So actually it's a percentage of less than high school. Okay, so the higher the percentage of the less than high school data, right, the percentage, then it's going to have a most important influence on the income. But basically, if when you show the feature importance, doesn't necessarily indicate whether that's positive or negative. So, and also you can see the next one is actually the third parameter, which is the age 0 to 4, right? So the percentage here also has a pretty significant influence. But we can basically plot these two data and then see what's the influence, right? So we said that the most important parameter is actually from all of these feature analysis is going to be the last one. So we can just plot the last one, right? So we can do plot data and -1, which is the eighth parameter, and then data, and let's use circle as a marker. Right? So then this plot basically shows you the correlation, right? You can see that basically the higher the percentage of less than high school degree, actually the lower the median household income, right? So it's identifying that the percentage of or the education really plays a role in determining or in associating with the median household income, right? And then but it doesn't necessarily lead to the causality. Basically, you cannot really say that it's because of the education that leads to the lower household income. It could be also the other way around. Because you have a lower household income, then it's influencing the education, like the percentage of the education, higher education, right? So in this way, you can sort of identify the important features in, let's say, analyzing certain regression data. And if you have certain data related to the education, let's say a new data related to the percentage, then you can use this predicted result. You can use the predict function to predict what is the likelihood or what is the likely median household income, right? So these are several exercise problems related to the machine learning that we're talking about in this class. And you can feel free to extract more data and play with this machine learning or this decision tree. And as I said, decision tree is only one type of the machine learning algorithm. There are so many different types. But you can see that you can generate some interesting analysis from our data, right? So the machine is learning by itself. We're not imposing any of the equation, any of the calculation to the data. Okay, so finally, it's the review of our entire semester. And as you can see, we spent a little bit more than half of the semester talking about MATLAB, right? I think these could actually lay some good foundation for us to use this programming tool to solve, let's say, day-to-day problems. We talked about the built-in function and user-defined functions. We talked about plotting and data analysis. Symbolic mathematics. It can help us solve a lot of equations instead of using hand derivation. We can do interpolation and curve fitting, integration, differentiation. But you can even solve for partial differential equations. And then later on, or more closely to the later half of the semester, second half of the semester, we talked about the probability, statistical analysis. We talked about the probability distribution functions, the sample probability, right, standard error, and the t-test, which is quite important in our data analysis or environmental data analysis, right? So now we talk about the machine learning, which is also seen as a statistical tool, right? We're not introducing any mechanisms, physical mechanisms to the data. We're just letting the machine doing the trial and error to classify the data and then try to generalize some experiences, okay? So this is some additional, right? So we also talked about structure and repetition, input and output, so on and so forth. Let's put it over here. And then in terms of the exam, we're going to cover the components that are shown in the red font, and we're going to talk a little bit more in our class today. So that's it for this class, and let me know if you have any question. It has been great to work with everyone throughout the whole semester. So I hope that now you have some understanding of these computational tools, and you can also use that or use these tools to solve your problems in other engineering classes. Okay, thank you, and hope you have a nice break.